Okay, so let's go ahead and begin today. So today's topic is what a multiplexer is. It's also referred to as a MUX. And the multiplexer is going to be part of lab 3. So just like previous labs, after the Thursday lecture, you'll be able to do some of lab 3, but you won't be able to finish it until Tuesday because there's also something called the decoder that's part of lab 3. We're going to talk about that on Tuesday of next week. Okay. So there's quite a bit about a multiplexer, as you can see from what's up on the board. But I want to start off with just a few definitions. Okay, these 3 terms here, byte, word, and half word, as far as what they mean in the digital world. So first of all, does anyone know what the word byte with a Y means in the digital sense? 8 bits, exactly. Yeah, the word byte means 8 bits. Okay, then also in the digital context, there's this word word. Does anyone know what the word word refers to in the digital world? This is a little bit more harder because it's not a strict definition. Does anyone know? I wouldn't expect anyone to. Occasionally I have someone a little bit more advanced. What the word word means in the digital sense is how many bits a piece of data. So quite often a word will equal the number of bits that most registers. We're going to learn about what a register is later on in the quarter. But in most cases, a word is the number of bits that can be stored in most registers of a microprocessor. So on each table, I put this diagram, and please leave the diagram on the table because I need this for my section from 3 to 6 seconds. But this diagram shows the structural model of the microprocessor you build in CP233. And if you take a look at this diagram, you'll see that quite a few of the lines have a /32. What does a /32 mean on a line? 32 bits. So most of the data that's going around in this microprocessor is 32 bits. And the reason for that is most registers for that microprocessor that you build in CP233 hold 32 bits. So in CPE 233, a word is going to have 32 bits. Okay, but if you had a microprocessor that mostly had registers that could hold 16 bits, and that would be called a 16-bit microprocessor, well, a word would be 16 bits for that microprocessor. So, the number of bits a word represents, depends. It depends on the particular hardware that you have. Okay? Can you guess what a half word is? Yeah, it's just whatever a word is divided by 2. So yeah, in this case, it'd be 16 bits. So just a word divided by. Someone in my 8 to 11 section asked about this. If they had seen somewhere a nibble. Have you ever seen that in the context of a digital circuit? Can you guess how many bits a nibble is if a byte is 8 bits? Something less. And in fact, it's 4 bits. Nibble is like half a byte. You don't see nibble as much anymore because, microprocessors now and processing circuits in general deal with so much data and have so many bits that, 4 bits almost becomes irrelevant. But back in the day, back when I was an undergrad, that was right at the cusp of them going from 8-bit microprocessors to 16-bit microprocessors. This is like, mid-1980s time frame. So back then, when you only had 8 bits to deal with, a nibble was more relevant, right? But now a nibble is not really that relevant. Okay, but anyway, I just wanted to mention these definitions just because, you know, they're not only important for this class, but when you take 233 and any other CP class, you're bound to run into those terms. All right, so now let's talk about a multiplexer, which is also called a MUX. We're just going to go over some basics first, then I'm going to show you the logic gate circuit for a particular MUX of 4 to 1. And then we'll do a timing diagram, and then we're going to get into the Verilog code that you're going to need to model a MUX for Lab 3. But we want to start with the basics. So here's the symbol for a MUX. And the MUX has 3 inputs. Well, I should say the MUX has at least 3 inputs. At least 3 inputs. And most of your inputs are referred to as data inputs. So you always start with 0, because we always start with 0 in the digital world. So this is like our 0th input, and D stands for data. So D0, and you see I put a bunch of lines, and I use DN here just to represent that, you know, we could have 2 inputs, we could have 3, 4, 5, you know, up to, in theory, infinity. Okay, right, so we have these data inputs, and then we also have another input that's labeled SEL for select. Okay, so there's data input and a select input. Now a MUX always just has one output. Okay, so always one output. Okay, but it has multiple data inputs. And like I said, it can be any number, you know, 2, 3, 4, 5, 6, you know, up to infinity. Now, even though it can be any number, quite often the number of data inputs that you have on a MUX is equal to a whole number power of 2. So even though you can have any number of data inputs, a lot of times it will either be 2, 4, 8, 16, 32, and so on. Okay. Now, also, the inputs, as well as the data inputs, as well as the output, can be multiple bits. So the way I drew this, because I didn't put a slash with a number, you know, this would be a single bit. You know, all these data inputs would be single bit, and this output would also be single bit. But you could have a MUX where each data input is 4 bits. And if each data input is 4 bits, the output would also be 4 bits. Okay, so your inputs could be, you know, 1, 2, 3, 4, again, all the way out to infinity in theory. Okay, so, you know, you have a number of data inputs, and then each data input is going to have a certain number of bits. Okay, whatever number of bits a data input has, the output has the same number. Like you would never see data inputs with 4 bits, like an output with 8 bits. Okay, they don't make MUXes like that. Okay. All right. So, any questions? Yeah, because there's one other input, and this is a really important input. This SEL input. SEL stands for select. Okay. And the select input, its number of bits. Yeah, number of bits. Okay, the number of bits for the select input depend on the number of data inputs. If I have 2 data inputs, I'm just going to have 1 bit for my select input. If I have 4 data inputs, then I'm going to need 2 bits for my select. If I have 8 data inputs, I'm gonna need 3 select bits. So do you see the relationship? If I had 16 data inputs, 4 select inputs, select bits, what'd you say? Right, exactly that. It goes back to the number of values that you can represent with a certain number of bits is equal to the number of bits. Okay. And you see the reason we have that relationship between the select bits and the number of data inputs is because a MUX, it functions basically like a multi-position switch. You see, the select input determines which one of these multiple data inputs gets connected to the output. Okay, so the way you can kind of think of a MUX is like a multi-position switch, like a dial. Right? You know, like you have a dial and it's got all these different selections that you can make, and you take your hand and you just turn whatever you want to choose, right? Well, here the select bit is sort of like the hand that's choosing which input gets selected to be connected to the output. Okay, so we had a MUX, with 4 inputs. And S here is for select. And let's say, each input is 8 bits. Okay, so I have 4 inputs. Each input is 8 bits, the output is 8 bits. How many bits would I need for my select input in order to choose between 4 things? 2. Okay, so my select would be 2. What if I change the number of bits that each data input and output has to like what you would have in CP 233, which is 32 bits. Like, let's make these all 32 bits. What would my number of select bits be in this case? Still 2. Right? See, it doesn't matter the number of bits that the data inputs have and the output has when determining the number of select bits you need. The only thing that matters when you're determining how many bits you need for the select is the number of inputs. Yeah, so as long as I have 4 data inputs, it doesn't matter how many bits is each on each data input. It only matters the number. Okay, so this would still be 2. Okay, so if I make the select equal to 0, if I make it a 0, 0, the data that's on input 0, which is denoted with this D0, that's what the output would equal. Only the data D0 would be at the output. If I make the select equal to a 1, 0, 1, the data on input 1, okay, D1, is connected to the output, and so on. So you see how it's sort of like a dial, if you will. The select is like the electronic hand that's selecting which one of these gets connected to the output. Okay, so any questions about that? Get a general idea. Now, you're going to be doing a lot with MUXes. So, I mean, if it's still a little fuzzy, I think by the end of the class, I think it will hopefully be clear. But do you have a general sense, Okay. All right, well, look at this diagram that's on the table. That's the diagram for the microprocessor that you build in CP233, and tell me how many MUXes are in that microprocessor. How many MUXes do you count? So how many times do you see this symbol? You're not going to be graded on this. Oh, I see somebody with 4 fingers. So 4. Yep, that's how many I count. 4. Everybody count 4. Because there's 2 muxes over by this ALU. One's at 2 to 1. Oh, I forgot to say that. We always, the way we specify a mux is we'll say the number of inputs and then the single output. So, this is a 4 to 1 mux here that I drew. Because there's 4 inputs and there's always 1 output. So you got a 4 to 1 mux at one of the inputs of this ALU, you got a 2 to 1 at the other input. There's another 4 to 1 up here by this thing called the reg file. You're going to learn about what all this is in CV233. But then there's a 6 to 1. At least I think there's 6. Yeah, there's 6 inputs on this mux over here where the PC is. So if I have 6 inputs, how many select bits am I going to need for 6? Because that's not a whole number power of 2, right? Still need 3. Right, because if I only had 2 select inputs to that 6 to 1 mux, I could only choose 4 of the 6. Right, if I have 3, I can choose 8. Now there's only 6. Right, but I can still choose 6 because I can go up to 8. All right, so the main reason I brought this diagram with me today is just to show you, what you're learning in this class does apply to, the following. Okay, because you'll be using muxes. You'll hear the word, and byte, half word, and all that. It takes you to you also hear it in this class a little bit too. All right, so the next thing, unless there's questions, is to look at the logic gate diagram of a mux. And this is an example of a 4 to 1. Okay. So this 4 to 1 mux, the way it's made with gates, and look, you got 4 AND gates. We got an OR gate, we got a couple of inverters. So here's a review question, a pop review question. What kind of logic circuit format is this? Is this NAND, NOR, SOP, POS? Which of those SOPs? SOP what?
Because it's 4 gates feeding or AND gates feeding into an OR gate.
Right. So the AND gates are giving us the product, right? And then they're being summed with the OR gate. So yeah, this is an example of an SOP, sum of products. Okay. And you can see that the AND gates have 3 inputs each. And over here, these are the data inputs, D0, D1, D2, D3. So, just like I labeled D0, D1, D2, D3 here, now we're taking this symbol for the mux and showing like what that symbol represents in logic gates. Now, before we actually analyze this logic gate circuit to come up with the truth table, let's look at the truth table of an AND gate. Now, here's another review question. Is an AND gate a universal gate? Remember we talked about universal gate? Is an AND gate universal? No. What gates are universal? There's 2 of them. Which 2 are universal? That's one. And NOR. Right. NAND and NOR, those are your universal gates. And what do we mean by a universal gate? Like, what does that mean? Exactly. Like you can use a NAND or a NOR to make any other gate, right? Remember how we had an activity on that, right? That use a NAND to make a NOT, a NAND to make an AND, a NAND to make a NOR, and you can make that. So take a NOR and make a NOT gate out of it, or an AND gate, or an AND, right? So, okay, but yeah, AND gates are not universal. Only NAND and NOR are universal. Now, the other thing you might remember when we were talking about universal gates is that I talked about how it's important to be able to understand a truth table. Right? Because, in the past, students have asked me, they go, oh, will you give us truth tables for the midterm? And I'm like, well, whether I give you the truth table or not, whether I actually give it to you or whether you remember it, what's really more important than the truth table itself is understanding the truth. And often people have trouble with that because they're like, what's to understand? There's just zeros and ones, you just look at the row, you get the output. Well, understanding a truth table, again, an example is the following. I gave an example when we were talking about universal gates, when we had the NAND and the NOR. Well, here's another example of understanding a truth table by using this AND gate. If I just divide this truth table in half, okay, where you see the blue line, and then I only look at the top two rows. Can you see what the top two rows are telling us? Because if I make one input to an AND gate at 0, what can I say? If I make one input to an AND gate at 0, what can I say?
No.
The output's going to be what? Yeah, it's going to be 0. See, if I make one input to an AND gate at 0, it doesn't matter what the other input is. Regardless, the output's going to be 0. So, if I have an AND gate with 18 inputs instead of just 2, and just one of those 18 is a 0, I don't care what the other 17 are. The output's going to be a 0 anyway. It'd be a waste of time to figure out what those other 17 AND gate inputs are, because they're not going to matter. Okay, but look what the bottom half of the truth table tells us. What does the bottom half tell us? Well, yeah, that's what the last row tells us. But what if you put these two rows together and say, okay, if one input to a 2-input AND gate like this is a 1, the output. Yeah, the output just equals the other input, right? Yeah, see, so if one input to a AND gate is a 1, the output's going to equal the other input. Okay? So again, that's an example of what I mean by understand a truth table. And now we're going to take our understanding of this truth table and use it to help us do the analysis of that gate circuit for the MUX. Okay? All right, so we're going to come up with a truth table for the MUX. We're going to find what the output F equals when the select bits are these values, 0, 0, 0, 1, 1, 0, 1, 1. Now, we're probably not going to do all the rows. In fact, I think after I do the first row, you'll get the idea. But, if you want me to do all the rows, I will. But we'll start with the 0, 0. So S is 0, or S0 is 0, and S1 is 0. So you see these bits here, those are the select bits. So those are the select bits. Our select input. Oh, I forgot to actually write the 2, but like we said earlier, this would be a 2. Well, no, I'm sorry, I wrote it over there. Yeah, we didn't say how many inputs here. I wrote it here. So yeah, 4 inputs, so 2 select bits. Okay, so both bits are 0. So we have this inverter. So what am I going to have at the output of that inverter? A 1, right? Because it's going to invert the 0 at the input and make this a 1. So there's going to be a 1 at this top input of this AND gate. There'll also be a 1 at this input, okay? Because this input of this AND gate is connected to the input of this AND gate. Now, before we go further, I should point out that where lines cross, right, like here and here, here and so on, there's no connection. Okay, if there was a connection, there'd be a dot. In old diagrams, so this is back in the day. I don't think they do this much anymore. But in old diagrams, you'll see this. You'll see like a little hump. And that's just to emphasize that there's no connection at that intersection. Okay, but in most diagrams nowadays, they don't do the little hump. It's just understood that if there's no dot, there's no connection where they cross. Okay, so because of this inverter, I'll get a 1 here, I'll get a 1 here. Now, if you look, this line here doesn't go through an inverter. So that will put a 0 at the input of this AND gate. And like we just talked about, if you have a 0 at the input of an AND gate, it doesn't matter what the other inputs are. The output's going to be 0 regardless. So you see, by understanding a truth table, I don't have to find what these inputs are because they're not going to matter. Okay. Let's see. Likewise, there's going to be a 0 right here. So the output of this AND gate is going to be a 0. Okay, so now we come over to S1, right? S1 is also 0. And if you follow this path down, you'll see that this goes to this input for that AND gate. So since that's a 0, I know the output of this AND gate is 0. Okay, but now just like we said over here, this inverter is going to take the 0 at the input and make it a 1 at its output. And then that 1 is connected to this middle input of this top AND gate. So now look at this top AND gate. It's got 2 1s, and then the other input is D0. D0, that's the data. D0 can either be a 0 or a 1. See, all these data inputs can either be 0 or 1. So what is the output of this top AND gate going to be? 0. Yeah, just D0, right? Because if D0 is a 0, that's going to make the output a 0. If D0 is a 1, that's going to make the output a 1. So does everybody see that the output of that top AND gate is going to be D0? Whatever that data on the D0 input is, that's what we'll have at the output of that AND gate. All the other AND gates are going to be 0. And now if you look at the input of the OR gate, well, it's going to have a 0 on this input, a 0 on this input, a 0 on this input, and then this input's going to be D0. Right? So you got 3 inputs equal to 0 to the OR gate, and then this input is either going to be a 0 or a 1, right? If D0 is a 0, it's a 0. If D0 is a 1, it's a 1. Well, how do OR gates work? Yeah, it's like a summation. So when do I get a 1 out of an OR gate? Say that again? Yeah, at least 1 1, right? The only time I get a 0 out is when all the inputs are 0. So you see when D0 is a 0, I'll get a 0 out. When D0 is a 1, I'll get a 1 out. So that means our output is just D0. Okay, so you see, when the select bits are both 0, we're going to get the data D0 out. And that's exactly what we were talking about when we were talking about the function of a mux, when we were looking at the symbol, right? We said if the select is a 0, the data D0 will be at the output. And if you went through the same analysis for these selected values, you would see that 0 1, we get D1, 1 0, we get D2, the 1 1, we get D3. I mean, does anyone want me to do another row, or do you trust that we would get this, or want to do it on your own and prove it to yourself? All right, so you see this again was a little bit of review, right? Because we're using analysis with gates like we did earlier. Okay, so before I move the camera, do you have any questions thus far? No? Okay. So let's come on over here. I might move your sneaker there. Let's go a little further, I think. Oh, there we go. All right, so the next thing is I wanted to show you an example of a timing diagram with a mux. And the activity today is doing something like this. So if you understand this example, then I think the activity should be fairly straightforward. So, okay, so what kind of mux is this? So what to what? Yep, 4 to 1. There's 4 inputs, 1 output, and there's always 1 output. This is a 4 to 1. And you can see each input has 8 bits, the output has 8 bits. How many bits would the select input have since we have 4 inputs? 2. And now here's our timing diagram. So you've seen timing diagrams now, right? Because that's how you verify your designs on Vivado. So you know that on the left, that's t equal to 0 and time progresses as we go left to right. So we're showing all our inputs here and we're gonna figure out what the output is. Now there's some, there's a symbology here you haven't seen before. It's the 0x. You know, it's 0x3, 0x1, 0x24, and so on. 0x is just another way of denoting hex. Okay, so whatever follows, and whatever's after the 0x, that's in base 16 in hexadecimal. All right, so this is equivalent to, you know, the 0x is equivalent to, you know, when you put a subscript 16 for first day of class, when we were talking about different bases, we said, well, you know, if you have like a number like 24, well, to denote that as a base 16 instead of base 10 or some other base, you know, we put a subscript 16, right? Okay, so that's what the 0x means. It just means what's following is in base 16. It's hexadecimal. All right, so let's figure out what this F output is. So just like we've done before in timing diagrams, you start at the left at t equals 0, and you have to evaluate every time there's a change in input. And that's what, you know, that's what this hex is. This is showing that this is changing from 3 hex to 1 hex, right? This is showing that this is changing from 24 hex to CF hex. Okay, but let's draw a line here. Okay, so on the left of this blue dashed line, that's when the select input is a hex 3. That means our select is a 3. So what is F going to equal if the select is a 3? Okay. Right. See, it's going to equal data AA because data AA is connected to input 3. So I did this on purpose where over here, I labeled it input 0, 1, 2, 3, but here I labeled the inputs 3, 2, 1, 0 because it doesn't matter what the order is, the operation's the same, right? No matter how you order these or how you draw in the symbol, the inputs, if the select is a 3, it's going to choose the data on the 3 input. Doesn't matter where the 3 input is drawn. Okay, so AA is a 24 hex. So you see that's what our F would equal. Be a 0x24. Okay, so now the select goes from a 3 to a 1. Right here, F is going to change because the select input changed. So what am I going to get at the output now when the select goes to a 1? Right, you're going to get the data CC. And look, data CC changes at this point. Right, so just when the select changes from a 3 to a 1, the output is going to equal 22 hex. So it would be 22. And then it changes to A3 hex. So right here it would be A3 hex. Okay, and then you look at the next time. Okay, the next time the select changes, it goes from a 1 to a 0. So now the output is going to equal what? Going to equal data DD, right? Because that's the data connected to the 0 input. So now during this time here, let's see, what is DD equal? It equals 2A hex. And then right here, it's gonna change to FF. All right, so you get the idea. Could you finish this? All right, you can see it just changes to a 1 again. So during this time, it's going to equal CC, right? It's going to equal this data, and then it goes to a 2. So during this last time here, it'll equal the data on PB. Okay, so do you see how, again, it's acting like a multi-position switch, right? The select input determines which one of these multiple inputs gets connected to the output. Okay. All right, so like I said, the activity there, I think there's like 3 different tiny diagrams that are along the line of this. So you'll get more practice with this. All right, so let's see. Should I turn the camera? No, I guess I don't have to turn the camera till I get over this. All right, the next thing is I want to show you the System Verilog code, or an example of the Verilog code that you're going to need in order to model the MUX. Okay, because up until this point, what we've been doing is we've been using Boolean expressions to model hardware, right? Lab 0, Lab 1, the lockbox, and also when you did the half adder and the full adder for the RCA, you were using Boolean expressions along with an assign. Okay. But starting today, and for the rest of the quarter, and when you take the next class, CP 233, we're going to start showing you code that now you're going to let Vivado do the work. Okay, instead of you coming up with the Boolean expressions from a truth table, we're going to start using if statements and case statements to model our hardware. Okay, and for the MUX that you'll be designing for Lab 3, we want you to use an if statement. Now, I'm going to show you an example of an if statement in System Verilog that models this piece of hardware called a comparator. Okay, so I want to emphasize what I'm about to show you is an example. You're not going to have a comparator in Lab 3. In fact, you're not going to have a comparator in any of the labs this quarter. Now, depending on what you decide to do for a final project, you may need a comparator then, okay? And this example of an if statement for a comparator, it's more complex than what you need for the MUX for Lab 3. Okay, so if you understand what I do here for the comparator, the MUX is much simpler. Okay, I think it's better to show you a more complex example than what you have to do than show you more easy examples than what you have to do, okay? But sometimes students don't believe me and they think they have to make it complex. But anyway, so here we go. And I do need my notes for this so I don't make so many syntax errors. And I can't guarantee that all the syntax is right, but most of it should be. And my purpose of showing this is more like the format of the if statement, not so much, the syntax. Although, like I said, most of the syntax should be right. All right, so like any module that you've been doing, you start off with a name. So you can see I started off with calling this module comparator. And then you're going to declare inputs and outputs just like you've done before. Now, notice this is our black box diagram, right? Our main inputs and our main outputs. So this comparator has 2 main inputs, A and B. Instead of putting a number here for A and B, you know how many bits I'm doing this in a general sense. So that's why I just put the number sign, because what I'm about to show you is the same no matter how many bits A and B are. And then we've got 3 outputs, GT, LT, EQ. They're all single bit. Can you take a guess what GT, LT, and EQ stands for, since this is a comparator? A comparator is going to compare these 2 numbers at the input. So can you guess what those greater than, less than? Yeah, it's just greater than, less than, or equal to. Thanks. So you're going to have to declare your input just like you've been doing. So for example, input, since it's multiple bit, you'll need the square brackets. Now, again, I'm doing this in a general sense. So whatever this number is, you would put that number -1 for your high number. Right, and then you put 0, because we always call the least significant bit 0. So, you know, if this was 8 bits, right, you put 7 to 0. That's why I put the number -1. You know, in like a, and let's see, it's a comma instead of a semicolon. And again, I'm not going to put everything on here, you know, because you'd have to define input B the same way. Now, your outputs, so, you know, you have another line. For your outputs, you put output. Now, there's something different that you have to do in this case that I'll come back to. So I'm going to leave a space here, okay, for a reason, because I'm going to come back to it. But then I'm going to put, you know, our outputs GT, LT, and EQ. Okay, and then you would, you know, like close the parentheses, put a semicolon. Okay, so like I said, I purposely put a space there because something goes there that I'll show you coming up. All right, but here's where it gets new. When you use an if statement in System Verilog, the if statement has to go in what's called an always cone block. Okay, so the next thing we would put after we declare our inputs and outputs is we would put always underscore COMB. Okay, COMB is short for combinational. See, all the circuits we've been looking at this quarter, even though I haven't said it previously, all the circuits are combinational. And what's meant by combinational is logic circuits that have no memory. In about 2 weeks, I think it's right before the midterm, that's when we'll start talking about memory. Okay, circuits that have memory. And circuits that have memory are called sequential. Okay, sequential circuits. And you'll see when we get to that part of the course that the thing I've been telling you, that if you see it in a warning, treat it like an error, that word latch. Well, a latch is like the main part of a memory circuit. And that's why, you know, for the first 2 labs and also, or first 3 labs and also, you know, the next couple of labs, if you get a warning with the word latch, that's why I want you to treat it like an error, because if you, in your Verilog design, if you have something creating a latch, that means it's creating memory. And we shouldn't be getting any memory because we're doing combinational circuits here. Okay, so anyway, I'll talk more about that, like I said, when we get to sequential circuits in a couple of weeks. All right, so we got this always poem. The next thing is you have to put begin. Okay, this is the begin for this always poem. And now you do your if statement. So you go if, and here, since it's a comparator, we're going to say, okay, if A is greater than B, and you got to put another begin. Well, if A is greater than B, output GT is 1, output LT is 0, output EQ is 0. And then we have to put an N that goes with this begin. So, okay, this N and this begin go together. This begin is for the always home, and the N for that's going to be later on. Okay. So your if statement, it can have either 0 else if, or it can have as many else ifs as you want. Okay. Now, if you don't have an else if, you have to have an else, except for something we're going to get to in a few weeks. Okay, but right now, if you don't have an else if, you got to have an else. Okay, but here we do need an else if because we've got more than 2 choices here. So the next thing we would do is go else if. And I'm pretty sure this is all one word. I don't think there's a space. I'm pretty sure. But if you get a syntax error, it might be there. Then we're going to say A less than B, And we need another begin. All right, so if A is less than B, GT is 0. LT is 1, EQ is 0. And then we need an N for that begin. Okay, else. And we need another begin. Else GT equals 0, LT equals 0, EQ equals 1. Because obviously, if A is not greater than B or A is not less than B, well, then it must be equal. And then we need an N. Right? This N is for this begin. And then we need an N for this begin. So you put another N. And then you would N module. So a lot of times where you'll get errors is you got to make sure you have an N for every begin. So sometimes like people will have an extra end or they'll miss an end or something like that. So watch out for that. You have a question? Does what matter? No, it doesn't. It's for readability. It's a good idea to do it for readability, but white space doesn't matter in system Verilog. So you can have as many space, as much white space as you want, or as least white space. But I always recommend using indentation just for readability. You've probably heard that before, I would imagine, in your other programming classes. Okay, now I'm going to show you another way to do this. But before I show you another way, do you see the basic structure of it? That again, I may have some syntax errors. I wasn't like really careful. I mean, I have it in my notes here and I think it's basically right. But the big thing is, again, you got to have the begins and ends that match up. And yeah, you just list your outputs as you can see here. Okay, so everybody good up to this point? Well, let me show you another way. Another way to do this is that we could initialize all our outputs to a certain value and then just show the output that changes within the if state. You see, if I only have one output within the structure of my if, then I don't have to put these begin ends. You see like this begin end here? The reason why I have to put this begin end is because I have more than one output. Same thing here, same thing here. See, if I initialize my outputs to a value to begin with, and then I start my if statement, well, then all I have to do is just put the output that changes. And if I just have a single output that's changing, I don't have to put the begin end. Okay, so I'll show you what I mean by that. So to initialize values, you do this. You just go initial. Need a begin for the initial. And then, I could just set everything to 0 to start. GT 0, LT 0, EQ 0. And end this. All right, so this initializes all my outputs to 0. Okay, then I do my always comb, always underscore COMB, and I have the begin for that always comb. And now I would just have if A less than B, GT equals 1, else if A greater than B. Oh wait, I got it backwards. Sorry, this is grading. This is this. Okay, yeah. If A greater than B, right? Same as what we have here. We want GT to equal 1. If A less, else if A less than B, LT would equal 1. Else EQ equals, and then we would just have to end this begin and then end module. Okay, so you see, when you have multiple outputs, if you initialize the values first, and only one of those outputs is changing, then you can get by without putting this begin end here. So I don't know, it looks a little more compact, doesn't it? Have a question?
Oh, yeah, so we can do that same for A,
Do the same for what?
for like, how do you know it's A?
Well, you're gonna declare your inputs and outputs like any module at the beginning. So yeah, you declare, input A is so many bits, input B is so many bits. So yeah, that's how it knows like what's an input, what's an output is, yeah, you gotta declare it just like what you've been doing, in your other, your other models. Yeah. Yeah, again, the new thing here is, if you're using an if statement, it's gotta go inside the always comma. Oh, I almost forgot. I gotta come back to this, right? Remember I said I left the space here for a reason? Okay. When you have an output or outputs within an always comma, you can't just put output and then the names like you've been doing. You have to put logic in between output and the names of the output. Okay, you only have to do this when your outputs are within an always comma block or an always FF block that we're going to get to in a few weeks. Okay, see, you haven't been doing this previously because you weren't doing an always comma, right? You don't have an always comma, you don't have to do that. Okay. Also, this was a question that came up in the other class, and I'm glad the person asked it because it put it in my brain so I would remember to tell my other sections, because if I don't say this, usually somewhere along the line someone discovers this, and that's, remember the assign that we've been using, like with our Boolean expressions, right? We've been doing assign, and then remember in the activity last class when you had to draw the diagram from the structural code, and you saw some assigns there, like assign this input or with another input. Remember all that? Well, assigns cannot go within an always comma block. Assigns have to be outside an always comma. I mean, typically assigns are in the structural model where you're making the connections. Okay, typically you don't put assigns, although you could. I'm not saying you can't, but typically you don't usually see assigns in like lower level modules. Okay, you see it in the top module, the structural model that you're making all the connections. Okay, but they definitely can't go within an always comma. And I think in the past, if I remember right, students that have done that have put an assign within an always comma, I don't think all of the time do you get an error. Like it will actually go to synthesize and generate the circuit, but when it does, there's going to be an incorrect circuit and it's not going to work the way you want it to work. Okay, so turn the camera now. We're a little bit past the top of the hour, but I think it's only going to take me like another 5 minutes to finish. So I think I'll just plug along unless somebody's really adamant about taking a break. You're okay if I finish up here so you can get started with your work? All right, so for lab 3, there's 2 parts to it, just like, the previous labs. And we're doing part 2 before part 1. See, I had that over in the agenda. We're doing part 2 today. We'll do part 1 Tuesday. So part 2 of lab 3 is design this mux and test it, right? Simulate. So this is a 2-to-1 mux. Right? See, there's only 2 inputs. Again, muxes always have just 1 output. Each input and each output has 4 bits. So since I only have 2 inputs, 2 data inputs, how many bits for my select? Just 1, right? Because if select is a 0, data A will be connected to the output. If select is 1, data B will be connected to the output. Okay, so we want you to model this 2-to-1 mux using an if statement. And the if statement that you need is a lot simpler than that example. Okay? Because what's going to be the condition in your if statement? Because what's determining which input gets connected to the output? The select. So, if select this, output equals this. Else, output equals the other. Right? And you see it's a simple if statement. Yeah, I'm just emphasizing that because I think sometimes because I did this example, students think it has to be like this, right? But again, this is more complicated than what you need to do for this 2-to-1 mux. Okay, again, I showed you this, for the structure, and also, later on in the course, you'll be getting to, if statements where you might have to do more like that, okay? But today, the if statement should be fairly straightforward. So what you can do today, after you finish the activity, what you can do today, create a separate project for lab 3. Hopefully you've been doing that for all the labs, like I suggested at the beginning of the quarter. And then just do a design source that has the if statement for this 2-to-1 mux. Then you'll need a sim file. How many test cases are you going to need to make sure that this 2-to-1 mux is working the way it should? What's the minimum number of tests? Yeah, 2. You just need 2 test cases, right? Because you'll have, your test cases will be A equal to 4 bits, B equal to 4 bits, select equal to 0. A equal to 4 bits, B equal to 4 bits, select equal 1. And when it's 0, you should get the data on the 0 input. When it's 1, you should get the data on the B input. You can make the data whatever you want. Make them different, right? If you don't make them different, you're not going to know which one it's selected. Okay, but yeah, just 2 test cases to make sure this mux works. And then the other thing you can do is in lab 3, we're going to be using the ripple carry adder that you designed in lab 2. So you can just bring over your RCA design source file for the RCA, and also you'll have to bring over your half adder design source and your full adder design source because they're part of the RCA. Okay, but you don't have to bring over the sim files because you already, simulated your RCA and provided it was good. Your RCA works. Okay. So that's the most you can do with the lab before Tuesday is just get your mux working. And then on Tuesday next week, we're going to talk about what a decoder is. And we're specifically going to talk about a 7-segment display decoder. Okay, on your basis board, you have 4 7-segment displays. Lab 3, we're going to start using one of those displays. Okay, so on Tuesday, after you learn what a decoder is, you'll do a design source for a decoder, and there you're going to use a case statement. Okay, because in System Verilog, you can also model with a case statement. So you'll get some practice with a case statement for the decoder. You'll also have to simulate that, make sure the decoder works. And then you're going to have a structural file that connects those modules together. You'll have an RCA, a decoder, a mux, and you're going to connect them up using a structural file, just like the RCA, right? With the same kind of coding that we talked about for the RCA. And what this circuit will do is that it will take the addition of your RCA and display the result on a 7-segment display as a hex character. Okay, so that's where we're headed. Okay, so I told you it would only take about 5 minutes, right? So it wasn't fibbing to you. So do you have any questions before you get started with the work today? Again, you want to do the activity. Everyone should have an activity. Did I put the activity up? Yeah. If you don't have an activity handout, let me know. There's 3 timing diagrams to work on. And again, once you're done with that, you can start working on lab 3.